My fabulous chemistry faithful, video number 4, PBoM, coming at you from a new recording location. Because that's what happens when your winter break gets extended, right? So I can identify phase changes in heat using heating and cooling curves. Basically, this is going to be the task. Well, you need to be able to draw these two pictures perfectly. And notice they are always set up as 3 slants and 2 flats, right? So there's a heating curve, starts low and goes high. There's a cooling curve that starts high and goes low. That's really the bulk of it. And then we can track what kinds of changes are happening once we make sure we know about kinetic energy and potential energy. So here's where those are all going to come into play. We'll draw it, label it, and we'll be on our way. So this heating and cooling curve is going to plot the temperature over time while a substance is constantly heated. Bang. The kinetic energy, of course, is when temperature is changing, because kinetic energy is heat. When the heat is changing, the temperature is the measure of that heat, so that will also change, right? So this is going to happen on the slants. That's these guys. See the 3 slants in the graph? Those are the 3 slants. Notice where we've got temperature on the y-axis. So when that is changing, the temperature is changing, therefore the kinetic energy is changing. And this is where we get into some of the stuff about phases that maybe expands on our prior knowledge, right? So potential energy now is changing on the flats. And notice it's saying gas to liquid. So there's this equilibrium going on here where there is a point in time where the heat you're adding or taking away no longer changes the temperature of said stuff. Like particularly, you would know this in the boiling point of water in the upper chart. Once you get that water boiling, it is now becoming into a place where it's actively boiling and it's changing phase at the top into gas. Now, if it was a closed container, you could save all that gas and keep it. And then once it all got converted to gas, then in the gas phase, we could raise its temperature further. But until it gets converted into gas, that kinetic energy is being transferred into potential energy. So that is just an example. There are some things about this unit that you do know, and that's going to help us make sense of these things. That's also happening at the other flat and then the other direction, right? So heating it up is boiling, while cooling it down is condensation. And when you start condensating that gas back into the liquid form, it's going to be at that temperature, 100 degrees. And you can't get it to go colder until it's all into the liquid phase. This happens at the solid to liquid phase also, which is melting and freezing. Things you know about. Definitely things we want to happen. Like today's the warmest, second warmest day of the week. It's melting out there, which is something we want. So when you're doing these things, straight up, 3 slants, 2 flats, don't even worry about what it's saying it should be over here on the right and left hand side. Don't worry about the axes, right? It's temperature, it's time, and as far as numbers go, just draw the thing. Bop, bop, like this. Just draw the thing. It's heating. This is a heating curve, so it's got to go from hot to cold. As soon as you see heating, you know it's got to start low and go high. 3 slants, 2 flats. Here we go. Now we can label these things up. And this is what's important. This is where you really got to pay attention. This is breaking down those pictures on the last slide. So bottom slant is the solid phase. Straight up, always. Bottom flat is the melting phase. Because I'm heating, I'm going from cold to hot. It's going to be melting in this direction. This will be labeled a different phase change because I'm cooling in a minute. It'll be very much the same. This video is dragging out, I know. Notice that spot is the temperature of the melting point. So if we were doing water, we could go ahead and, if we were labeling up this substance as water, we could go ahead and put that 0 right there. 0 degrees Celsius is the melting point of water, right? The fixed points on the thermometer. It's going to come up a lot. Center slant, liquid. And then the top flat is going to be the boiling point, specifically, again, because we're adding heat. And notice we can see what that boiling point is in temperature measurement on the left-hand side. So we put 100 degrees Celsius there. if this, again, was water. If it was something else, we'd have to put its boiling point there. And that number can change. If the stuff is not water, it's not going to have 100 degrees boiling point. So boiling point of water is 100 degrees, not of everything. Gas, phase, top, slant. I'm going to go ahead and do the cooling curve, I think, now. Oh, wait, check it. You got to know these too. So on the slants is where the kinetic energy is changing. Every time there's a slant, you'll see a kinetic energy change. And when you see me write this on the board, I'm probably going to say delta KE. I'm probably going to put a triangle up because that means change in. So changing kinetic energy happens at all of these spaces. And then change of potential energy happens here. So this would be delta PE, okay, at the flats. Now I'm going to go ahead, hopefully, and do the reverse or make you write it all again first. So let's do that. And then we'll do the cooling curves, and then we'll be done. So melting point, lower flat, boiling point, higher flat. That's what MP/BP means. We've seen that in class. Solid is the lower slant, liquid is the middle slant, gas is the high slant. Got to know that. Whoopsies, went too fast. Liquid, solid and liquid is what's happening at the lower flat, the phase change, and liquid to gas, that equilibrium is happening at the higher flat. The intervals that kinetic energy is changing, that is the slants. So all slants. Interval show potential energy is changing, that would be all flats. Now let's do cooling curve. Go through this one a little bit faster. Cooling curve, start high, go low. 3 slants, 2 flats. Bop. Come on, 3 slants, 2 flats. There we go. And again, the top slant is going to be gas. The bottom slant is going to be solid. Let's see which one comes up first. We are cooling, so we'll start with the gas. Then we'll go to the phase change, which is condensation. And this would be the condensation point. Middle slant, again, will be liquid. Sorry, I went through that fast. Getting to the freezing point, which is now the cooling curve version of solid to liquid. And then we got solid. And then again, at all 3 slants, the kinetic energy is going to be changing. So it's my hope that after this video, we got it solid. Like the kinetic energy is changing at the slants. Potential energy is changing at the flats. Good. We're going to write it all back out for a cooling curve. Yep. So finding the condensation freezing point. The condensation point is the higher flat. The freezing point is the lower flat. Where the material is solid only, liquid only, well, the gas is at the high slant, liquid the middle slant, solid the lowest slant. Again, notice I just changed the order of these because I'm cooling going from high to low. Okay, where is the material solid and liquid? Well, that's at the higher flat. That's where that phase equilibrium is happening. And again, at the lower flat, phase equilibrium changing. So that's where potential energy is changing. Kinetic energy is changing on all the slants. Potential energy is changing on all the flats. And now I think, no, we're not done. Close. Oh, by the way, I am going blind. I don't have the paper in front of me. Usually at my teacher desk, I'm sitting, I got the paper in front of me so I can see a little bit more, pace out where we're going with this. I'm doing this blind because I'm not different mug and everything. I'm not at school. Energy normally entering the system, substance is going to rearrange the particles into the next phase. The energy is not changing the temperature. This is endothermic changes during the phase change. Okay, during the phase changes of matter, the temperature is not changing, right? This is the energy normally exiting the substance and rearranging during phase changes. This is, again, the energy is not changing. Endothermic, exothermic is really about adding energies endothermic, so that's got to be on a heating curve. Heat exiting is got to be on a cooling curve. And then these are the way we make sense of what's happening during a phase change. And with that, we are now finally done. Yes, milk, stop.